Today is the day. Today is actually a really cool lecture. It's really sad that Jonathan left. I'm going to put his card on top and call him for the
Wait, did he leave or did he just use me?
He took his stuff.
He did?
And he wasn't even stealthy about it. Anyway, no, today's fun because today is largely conceptual. Not a lot of equations going on today. So you know how that is. You know, picture time. Stories. I love pictures. Okay. So before I get into, so we are going to officially begin our sojourn into curved space today. So everything we've been doing up to this point has been in flat space. That's the space of special relativity, or even Galilean relativity. So we're going to move to curved space. But before we get into curved space, I just want to remind you of a couple of very important things which hold true even in curved space. And these are the kinds of things which I worked really hard to get to sort of unroot from your preconceptions about, you know, oh, this is the case for this, and that, the other. Things that change when you go to special relativity from your more familiar context of Galilean relativity. So for example, oh wow, my markers are dead, that sucks. I didn't get anything written with that marker. Let's try these. Golden, all right. So in three-dimensional Galilean space-time, we have the following, the metric, and I'm just going to write the spatial metric. Really, Galilean relativity involves these two weird metrics that you can transform separately. But basically, the spatial metric, you're all aware, is just the identity matrix. And that means that in particular, the inverse of the identity matrix is equal to, or the inverse of the metric, maybe I should write it this way. In this case, the metric and its inverse have the same components, okay, because the inverse of the identity is just the identity. And also, and there was some persistent confusion about this last night, in this very special context, if you consider the components of vectors and dual vectors, they are exactly the same. So up until special relativity, you never really referred to vectors and dual vectors. You just called everything a vector. Why not? Everything's got the same components. Also, when you consider the paths of objects, you parameterize them with this universal invariant t. And so you can just talk about how the spatial position varies with time. And so those are some of the things that we encountered and we had to uproot when we moved to 3+1 dimensional, or 4D special relativity. And in 4D special relativity, we found that in Cartesian coordinates, the metric does take a particularly simple form. We call it eta mu nu, and it's just diagonal minus 1, 1, 1, 1. But we still have this nice property that the components of the inverse metric are the same as the components of the metric itself, because minus 1, 1, 1, 1 has an inverse that is minus 1, 1, 1, 1. But where things change is that the components of vectors do not equal the components of dual vectors. And I should say that when I write this stuff, I'm talking about a component at a time. So I'm saying the ijth component of the inverse metric is equal to the ijth component of the metric in 3D Galilean relativity, and the mu nuth component of the metric, inverse metric, is the same as the mu nuth component of the metric in special relativity. However, the components of dual vectors do not match the components of the corresponding vectors. And then we also found that when we wanted to describe the path of something, we had to find some new parameterization, and so we now track the path through space-time, parameterized by what we found to be conveniently the proper time or the rest time, or the length of the interval, or the length of the space-time path itself. Okay, so you might ask, what of these things is going to change when we actually go to curved space, when we're dealing with general relativity? And when we go to curved space, what we find is that in general, G mu nu is going to be more complicated, but in particular, it is going to itself become a function of position. So instead of being just mostly zeros with a few ones or minus ones sprinkled around, we're actually going to find that the metric is composed of functions. And of course, or not of course, but one of the things that is going to play a very, very important, or could be a very important pitfall if you're not careful, is that because of the complexity of these metrics, in general, the components of the inverse metric are not the same as the components of the metric itself. So it becomes very important when you write a matrix to tell me, is that the metric or is that the inverse metric? Because they're not going to be the same thing. Okay? Of course, if the components of vectors and dual vectors were not the same in special relativity, that is going to continue to be the case in curve space. Okay, things are just getting more complicated in curve space. And we're still going to find it convenient to parameterize the path of things through space-time in terms of some parameter, where on occasion we will have to forgo using the proper time to parameterize paths. In particular, if we're interested in the path of something that is massless, proper time is not very useful because the length of the space-time interval is always 0. Okay? So the new thing to really keep out for in terms of a pitfall is this. But the really new thing is this. Our metrics are suddenly going to become way more complicated. Now what's interesting, and what we'll find and refer to quite a bit on the way, is that a lot of this stuff is actually true even in flat space. A lot of the third line is true even in flat space. Okay? All of the nicety of special relativity and a lot of these properties follow from our choice of coordinates. That is, we use rectangular coordinates, and that's where the metric takes this particularly nice form. We could, however, choose to describe flat space in curvilinear coordinates, like spherical polar coordinates. If we choose to do that, then it turns out that even in flat space, our metric becomes functional. And then the inverse metric and the metric don't have the same components. So the technology you have to develop to work in curvilinear coordinates on flat space serves as part of the development of what you need in order to treat curve spaces. Okay? The difference being that in curve space, there's no way to simplify things like you can in special relativity by taking a particular coordinate system. Okay? All right. So that's probably the extent of the equations or mathematical expressions that I'm going to write today, and now we're going to get really, really conceptual. Okay. So the first question that one could pose is, do we really have to curve space-time? Okay, you have all heard the lore that general relativity replaces the force of gravity with the curvature, the warping of space and time, and then things are responding to the warping of space-time. And that sounds very sexy, but you know, you can ask, well, can't we do that with the other forces? Why do we do it with gravity and not electromagnetism? You know, what's so fair? Okay. All right. Okay. Could we just relativize, I don't know, what was in the Kool-Aid? Newtonian gravity. Because remember, general relativity is a generalization of Newtonian gravity. It's an extension of Newtonian gravity to a relativistic form. And so you might say, could we just like do the normal relativistic treatment like we did for electromagnetism? Okay, can we do that for Newtonian gravity? And then what you find is, well, let's start out reminding ourselves of one of the fundamental expressions in Newtonian gravity, and that is the force of gravitation between two massive objects. And so we know...
Dr. Forner?
Yes.
That's an equation.
Yeah. That's real cute. It's real cute. So remind me to come over there and kick you in the face with my foot really hard. Okay. So I would argue that that is simply an expression for a force. It's not really a meaningful equation in the sense that it's like something that you would not think was related to something else. And, whoa, they're equal. That's a law of physics. You know, it's the difference between this versus this. Okay, they're both equations. They have equal signs, but this is more of a definition. This is actually a contentful law of physics. But anyway. All right, yeah. I'm kidding. Yeah, I'm going to write some equations, and I apologize. I lied. I'm a liar. I'm a liar. So, okay. Now, this is, of course, the form of the universal law of gravitation that you were introduced to in Physics 1, maybe written just a slightly more sophisticated way. And, of course, one of the first things that we notice is that we've got two objects at two positions, and we've got some coordinate system. So we're setting up their position vectors. And the important thing to notice is that in this expression, everything's evaluated at the same time t. Okay, so what that means is that according to this expression and the way we worked with gravity in Physics 1, the gravitational force on this object, due to this object, depends on the instantaneous location of this object. So what that implies when you use this expression is that the gravitational force is somehow being communicated at infinite speed. Okay, action at a distance, if you will. You can actually take this expression and doctor it up and say that, okay, no, actually, the force of gravity or the interaction of gravity can only be communicated from one point to another at the velocity of propagation c. And you can put that into this formalism, but what you find is that if this is in fact the case, then circular orbits become unstable. Okay. You don't actually have to do the mathematics of that. You can actually just look at a pictorial diagram of stable orbits, all right, which you're going to do in your homework. Okay. So, but that's one thing that we're pretty confident of is the stability of circular orbits. And so just kind of naively taking this universal law of gravitation and putting in a finite, propagation velocity of gravity doesn't work. But we already know a theory which is very similar to this where things do work out. And now I will write my second equation. And that is, of course, the Coulomb interaction between two charged objects, which takes, of course, a remarkably similar form. Okay. And this, of course, suffers the same problem, ostensibly. You're trying to write down a force law which says that the instantaneous force between two charged particles depends on their instantaneous position. You use the same t in each of these expressions. But of course we know that, while this works for electrostatics, where things have just been sitting there forever, so it doesn't really matter if you think about where this was now or 15 minutes ago, the position hasn't changed, then it actually doesn't matter. Where do you run into problems with regards to finite velocity of propagation of effects? In electrodynamics, where you actually allow things to move. But you have all studied electrodynamics, and you know that when you go beyond electrostatics, you have to incorporate a lot more details into the story. So this gets fixed in electrodynamics with a whole host of effects. For example, you get magnetic fields become an integral part of the story. You get these Leonard-Weikert potentials, etc. And what you find is that the entire story ends up being perfectly consistent. Okay? But it's just a considerably more complicated story than the starting point with electrostatics. Okay? Now, that might harken back to what we have here, because this is, if you will, a gravitostatic expression, and we might say this is only applicable when things are sitting still and have been for a long time. Maybe if you take gravity and you do the similar thing that you do here, add in something like a gravitomagnetic force, maybe some retarded potentials, this and that and the other, then maybe gravity itself will come out to be consistent, okay? You can in fact do that. And generally speaking, all of the extra stuff that you have to add in really becomes, it's largely irrelevant. We can get away with the Newtonian approximation, of course, in the non-relativistic limit. But there are two really, really big problems with this program. First of all, it gives you the wrong answers. Okay? It gives you the wrong answers. We can compare to some of the astronomical data that we have. And if you just do sort of a relativization of Newtonian gravity by analogy to what we do with electromagnetism, then you can use that framework to do some calculations. And you won't get quite the right answers. It is a great approximation, though, okay, when things are moving slow compared to the speed of light. But it actually has a deeper problem. Okay? The deeper problem is that this expression and any relativistic generalization that we make of it, like we did with electromagnetism, critically hinges on mass as the source of gravitational attraction. Okay? And what that means is that this starting point and any relativistic generalization of it is going to be absolutely incapable of accounting for the fact that even massless objects feel the force of gravitation. Okay? So you really need a fundamentally different starting point than Newton's universal law of gravitation if you're going to develop a theory that can actually explain why even massless things feel the force of gravity.
If you do the energy mass conversion, does it still not even
Okay, so what we're going to do is so what we're really going. Geez, sorry. Thanks, Madison. I appreciate it. Still sick. So what we're going to do is we're going to think about something which might or might not have been pointed out to you as early as Physics 1, but hopefully at some point in your physics career. And that is we're going to meditate carefully on the equivalence of two kinds of mass. There is, first of all, the inertial mass of an object, the inertial mass being the quantity that appears where, Madison? Where does the inertial mass enter into your physics knowledge?
What?
Where does...
What do you mean where?
Yeah, in what part of physics do you see the concept of inertial mass?
This one.
Right, and where in Phys 1?
With forces? I don't...
With forces, but in particular in what expression?
F equals ma?
Yes, exactly. That's actually exactly right. This is the m that appears in F equals ma. It's actually it's inertia. Mg, on the other hand, is what we call the gravitational mass. This is actually a gimme, and Bree is going to be happy to tell me where we encounter gravitational mass in physics.
Gravity?
Yeah, it's the mass that sits in this formula. Now, I mean, hitherto you've always just said mass, and you've never really cared about the distinction. But if you think about it, the masses that appear in those two places, they play very different roles. One of them is providing inertia, the resistance to accelerate under a net applied force, even if you've got other forces acting. The other mass is determining the size of a particular force. Okay? In particular, we know that with electromagnetism, you still have inertial mass for objects. You still use F equals ma, but the force in question is not determined by a mass, but rather a charge. So some people might like to call this a gravitational charge, just to really make a distinction. Okay? But what's key, though, is that all experiments have evidence that those two masses, though they appear in very different contexts, are always perfectly equal for any massive object. And so we should think very hard about that. and explore its ramifications. And in doing so, we're going to get quite a ways towards the general theory of relativity. Okay? So we shall begin with what I like to call deep thoughts with Jack Handy. As I watch the light turn from yellow to green, no, from red to green to yellow to red,
I actually know these talking about.
and back again, I thought to myself, is that all life is? Just a bunch of honking and yelling? Anyway, you guys, did you not watch Saturday Night Live? Deep Thoughts with Jack Handy? It doesn't matter. Okay. Jack Handy. Okay. All right, so here we go. So we're going to start with stuff we know, it's old school, we're very confident in it. From considerations of Newtonian gravity and Newtonian mechanics, we observe the equivalence of gravitational inertial mass, which we can call the weak equivalence principle. Okay, that is mg equals mi. The mg coming from our expression for Newtonian gravity, and the mi being that which appears in the sum of the forces as mass times acceleration. Okay? Now I'm going to repeat in brief some of the formulas that I just wrote, because we're going to make an important observation based on this. So we know that we can write the force of gravity in shorthand, if we happen to know the gravitational field at a point, as the gravitational mass times the value of the gravitational field at that point. That tells us the force on that mass due to the presence of that gravitational field. And then we also, of course, know Newton's second law, where we sum all of the external forces acting on some system or some object with a mass mi, and then that gives us the mass times the acceleration of the object. Okay? This includes all forces acting. Okay? As I mentioned, the sum of forces on the left could include gravitational, electromagnetic, force of your face, I don't know, but it's every force in the problem, but the inertial mass still plays a role, where of course this is only gravity. Okay? Nothing weird yet. So now what we're going to do is we're going to take this and we're just going to do one small thing. And we're going to say, okay, what if there is only gravity? What if gravity is the only thing in the story? Then we discover that if the only force on the left-hand side is the force of gravity, then we can immediately write that mg, g, is mia. And this weak equivalence principle immediately implies that all things accelerate with an acceleration that is equal to the local gravitational field. Okay? This is, of course, something that you saw in the first week of Physics 1. And then we spent a lot of time after that first week of Physics 1 trying to unpeel you thinking that gravity was an acceleration. And now I'm going to come back in a very advanced physics course and tell you, yeah, we were right in the first week of Physics 1. We lied to you. Okay? All right, so everything should be relatively old hat. We've seen this before. Notice, this very simple statement, though, relies on this exact equivalence between gravitational and inertial mass. You get that cancellation. Okay. Now what I'm going to do next is I'm going to rewrite this weak equivalence principle in a slightly different way, because the way that I'm going to write it, which is more pictorial, it's more fun, is going to be a little bit more easy to generalize. Okay, so we're going to now consider what I might call the weak equivalence principle prime. Okay, again, it's based on this idea that all other forces aside, the acceleration of any massive object is just equal to the local gravitational field. And so in words, the weak equivalence prime is going to say the following, and I'll draw a picture. For massive objects and external gravitation, that is, we're only considering the gravitational force on an object due to objects exterior to it. We could, of course, imagine a very large object which has its own gravitational force acting on its constituents, but we're talking about only gravitational sources from external things. For massive objects and external gravitation, a uniform external gravitational field is indistinguishable from a uniform acceleration. Okay. That was a lot of words to say that. That's why we do math, right? I mean, to say this in words requires all that garbage. Of course, it's all the stuff that led to this, all right? Okay, let me draw a picture, right? Here we go. And to just have some actual physics to contextualize this, I want you to consider projectile motion as the sort of physics that we're studying in all of these little experiments. So we have on the one hand a laboratory with our bold scientist in the laboratory undertaking projectile motion experiments. And then what we're going to do is we're going to take that laboratory and we're going to sit it happily at rest on the surface of the Earth, where we know that there is a uniform gravitational field pointing straight down, and we know the results of this experimenter doing some projectile motion experiment. He takes a ball, he tosses it, and lo and behold, we get that characteristic parabolic trajectory indicative of simple projectile motion. Okay? And then we can consider a separate scenario where we take a lab, we take a person in the lab, and we've removed the Earth. No more Earth. Okay? However, what we're going to do is we're going to take the lab and we're going to give it an acceleration pointing up, which happens to be equal to negative the value of the gravitational field in the first scenario. Okay? Then when you get rid of the Earth and you've got a lab, where are you? You're in deep space. Okay? What the weak equivalence principle prime says is that the experiences of these two people will be the same. In particular, and you don't need me to convince you of this, if this person grabs a ball and throws it, he's going to see that ball undergo simple projectile motion. Okay. Now there is, of course, one caveat to this, and I sort of exaggerated things so that someone would hopefully catch on. Let's just pick a victim. Cara. What's the one thing I might need to be careful of if I'm going to say the experience here is identical to the experience here? And it has to do with something I kind of exaggerated in the picture. Well, let me make an argument in words, okay? I would argue that this thing is uniformly accelerating up, and that is identical to a uniform gravitational field pointing straight down in this picture. Does gravity in this picture actually point straight down? Where does it point? Where? Towards the Earth, but towards where on the Earth? The center. Okay, and since my lab in this picture is so ridiculously big, we notice that actually gravity would point a little bit different on different parts of the lab. Okay, so in fact, you cannot replace this situation with this situation if you have a big lab. Okay, so the only thing we have to add to this equivalence is that this only holds for small labs. That's actually going to become very, very important later in the story. Okay? All right. Well, what do you do after you've had some deep thoughts? You have deeper thoughts. Okay? And our deeper thoughts are going to take the weak equivalence principle in either form, but in particular in the weak equivalence principle prime form, and extend it to what is called the Einstein equivalence principle. This is literally something new. Okay? So the Einstein equivalence principle says the following. Here we go. For any objects and any forces except internal gravitation. So this argument can include things like electromagnetism and so forth. A uniform external gravitational field is indistinguishable from uniform acceleration. Okay. Yeah.
Does that have any conditions on it, like the weak equivalence principle, where you have to have a small lab?
Yes. So all of these are going to be predicated on the assumption of a small lab. Yeah. Yes, go ahead.
What's the difference between the assumption that the lab is small and the gravitational field is uniform? Because if you have a uniform electric field, or because in this case, right, you don't have a uniform electric field across the width of the lab, which is what we're considering, or is it still uniform because it's radial?
Sorry, say it again.
What's the difference between the condition that the lab must be small and the condition that the external field must be uniform?
Oh, no, that's what you're doing
Okay, cool.
with a small lab, is you're getting the external field to be uniform.
Perfect.
Right. And we're going to come back and revisit that idea in a lot of depth. Okay, so, all right, so Einstein equivalence principle. Alex, you had a question, or you just stretching? Okay, so what does Einstein equivalence principle get us? Well, it actually gets us to GR. Okay, but let me just show you some of the more immediate consequences that are maybe not as obvious. Okay, so pictorially it says the same thing. But what I'm going to do is I'm going to think about this equivalence, and I'm going to go this way. I'm going to think about something happening in this scenario, and I'm going to use the Einstein equivalence principle to infer an effect in this scenario, which might not be completely obvious. You ready? Technically, this still is projectile motion, but many of you would balk if I called it that. I'm going to give this scientist a flashlight. And I'm going to ask him to shine it towards this wall. So a stream of photons, if you will, come beaming out of this thing. What is going to happen to that stream of photons as they move across the lab to hit that wall? Remember, this lab is accelerating upwards. Are they going to hit the wall at the same height? No, the wall will have moved. Okay? And it's not just that it will have moved, it's that it will have moved with accelerated motion. But what we find is that the light in this scenario naturally falls as it traverses the room. We all on board with that? By the Einstein equivalence principle, the exact same thing has to happen here, where the effect has nothing to do with an acceleration. It's got to be coming from gravity. So the Einstein equivalence principle, which says that I can interchange these two situations, immediately tells us that even massless objects like photons or light should feel the effects of gravitation. Clearly, a theory based on this equivalence is going beyond any Newtonian gravity starting point. Okay? By the way, there's nothing weird about this picture. The only thing, in this scenario, the only reason why this observer actually sees the light doing something funky is because the observer, the person in the lab, is actually an accelerating observer. Okay. An inertial observer watching what's going on in this lab would just see the light travel in a straight line. Okay? Go ahead.
Oh, no, sorry.
You guys can't stretch in this class, not allowed. Okay, so that's weird. Deeper thoughts. So the Einstein equivalence principle is sufficient to formulate GR, okay? And that's really where we're going to hang our hat in terms of getting somewhere. But you can actually go further and formulate what is called the strong equivalence principle. So if Einstein went to the gym, he would have gotten to the Einstein equivalence principle, which basically says the following. The content is the same, except we remove that condition. That was the thing in parentheses that said except internal gravitation. Okay? Now, we're not going to have to dig into what is modified when you adopt a strong equivalence principle over the Einstein equivalence principle. I'll just tell you the merit of it. And that is, if you start out basing what you're going to develop on the Einstein equivalence principle, then there is a possibility, of course, of developing the theory of general relativity, which is what we're going to spend our time doing. But there are actually other things that you can develop. There's something called the Brand-Sticky theory, which is a scalar tensor theory of gravity, and then there's other possible variants of gravitational theories which emerge from the Einstein equivalence principle. However, if you instead say, actually, we're going to start with the strong equivalence principle as sort of our bedrock, you can only get to one theory, and that's GR. So adopting the strong equivalence principle or finding some evidence that in fact the strong equivalence principle should hold will single out GR as the only viable option. We're not going to worry about that. We're just going to work with the Einstein equivalence principle and just focus on developing GR from it. Yes?
Why did we instill the condition of accept internal gravitation in the equivalence principle in the first place? Like, why was that a caveat that was made?
We're not going to get into the details of that. It's by no means obvious or intuitive. But you can obviously forgo it and make a much stronger statement. I mean, this is the strongest of all the possible equivalence principle statements because it's just got no qualifiers. Okay. So we did deeper thoughts, deeper rest thoughts. All right. this is the part of this story that is going to bother people. And that's good. Alex.
What do you mean by internal gravitation?
So this is the gravitation of a, so you have an object that you're talking about, like I'm throwing a ball, okay? I'm only talking about the gravitational influences on the ball from external objects or external sources. I'm not talking about the gravitational force between parts of the ball with itself. Okay, that would be internal gravitation. Which is clearly not something that is really relevant for practical applications until you get to very large objects. I mean, it's true, it's there nonetheless, but it's pretty much ignorable until you get to astronomical objects. Okay, here we go. This is where people get really upset. All right. And this is the best part about this lecture is I feel like all Physics 1 students should watch this at the end of Physics 1. And they'll be like, my teachers were liars! Okay, so you might remember that in Newtonian mechanics and in special relativity, in fact, they share one common feature, and that is there is a prominent role played by these things we call inertial frames of reference. Okay? In Newtonian mechanics, Jonathan? 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 Jonathan?
Somebody call him.
Jonathan?
He's on a date right now.
Jonathan? And bring me the phone. Call him. Call him.
That's really.
Call him.
Do it!
Call him.
Do it again, you're cool.
I'm not cool.
He's on a date.
There's no service in this building.
He hopes.
But you can text.
It's not ringing.
Leave him a voice message and try to forever.
Oh no, it's ringing. He's not gonna answer. No.
No, why would she?
He's like,
Leave him a voicemail.
Jonathan. It's Professor Flournoy. I drew your card. So I felt like I needed to interrupt your date and ask you, what role do inertial frames play in Newtonian mechanics? Yes. Okay, good. And why are those frames important? It's almost like you're here. Yeah. Why do we need to make sure we're using an inertial frame? You can ask your date. Okay. It's close. It sounds a little fake. Okay, I'm going to let you go, but I'm going to tell you the answer before you go. We can only use Newton's second law in an inertial reference frame. Okay? Enjoy your day. Goodbye. Okay. First time for... So Jonathan kind of got a survey because his card I drew. Ryan. In special relativity, what is the importance of inertial frames? You can phone a friend. because you're actually here. Chase.
The laws of physics can be represented the same in any inertial reference frame?
Yes, the laws of physics should take the same form between different inertial frames. Okay, that was the starting point. That was the principle of special relativity that actually led us to most of the details of the theory. Okay. Okay, so the thing that I want to ask you now is, and this is where it gets really weird, how do we find inertial frames?
How do we find them?
Yeah, like how do we establish an inertial frame of reference? How do we define diffs? How do we, define. Yeah, how do we find? We give them a fine. Yes?
We have to assign a coordinate system by which to measure it.
Coordinate systems are going to be very helpful in providing a mathematical description, but we actually don't need a coordinate system. Well, you probably need a coordinate system in order to get your devices to actually register data that you can interpret, but you can actually answer this question without referring to a coordinate system per se. Any takers?
Is it based on acceleration?
It is, but it's actually based on one of Newton's laws.
First one.
Well, it's either the first, the second, or the third. It sure as hell ain't the third. Yeah, it's the first law. This is the importance of the first law. So let's remember Newton's first law, which tells us in an inertial reference frame, and remember this is the funny joke that we tell in Physics 1 where we say, Newton's first law is just a special case of Newton's second law. Ha ha ha! And the students are like, yeah, Newton, what a dumbass! And then we're like, no, no, no. Newton's first law is actually very important because Newton's first law establishes what an inertial reference frame is. In an inertial frame, an object experiencing zero net force. Going back to my Physics 1. Gotta put a vector sign of everything! Will move with constant velocity. Okay? So let's take this and use it. That's just the words, but like, how do you use it? So, so we can talk about net force, and we can say, oh, let's take an object and let's have 6 forces acting on it, and all the forces add to 0, so it's got no net force acting on it. But it's easier to just consider like one force. So let me establish that this works nicely with E and M, and let's just have an example. So let's take a parallel plate capacitor existing in flatland. I'm kidding. Okay, so we know that if this thing is large enough, it's going to generate a constant, roughly approximately uniform electric field pointing to the right. And then we know that if we take a charge, say a positive charge, and place it in the presence of that electric field, then this is going to feel an acceleration to the right. Okay. Now what we would like to do is we would like to explain the motion of this charge, the observed motion of this charge, using Newton's second law. Okay. So we've got an electromagnetic force. We've got Newton's second law. We want to use those to describe what's happening. But the catch is, we need to make sure we're making our observations from an inertial reference frame. So how do we do that? We do the following. We put a charge somewhere, we put an object somewhere in this system with 0 charge. Okay? The only force we're thinking about in this context is electromagnetism, so this is a deep space experiment. And then what we can say is the following. Ready? This is the way the light of reasoning goes. We know that this thing is experiencing no forces. Therefore, it is experiencing no net forces. If we look at this thing and we see it move with a constant velocity, then we are in an inertial reference frame. So you take something which you know is experiencing zero force, you observe its motion, compare it, or you observe its motion, and if it is exhibiting constant velocity motion, then that tells you something about your own reference frame, that you are inertial. If you looked at this and saw it accelerating, the only way that can make any sense is if you happen to be the one accelerating, because there's no reason this is accelerating. Okay? So if we look at this thing and we see it moving with a constant velocity, or at rest, it's just as good, then we know we're inertial, and we can use Newton's second law to describe the motion of that thing accurately. Okay? We good? Probably. What's the problem with gravity?
There's nothing that's not affected by it.
There's nothing that's not affected by gravity. We used to be able to say these weird things called massless particles don't feel gravity, but that's not the case. There is literally nothing that does not feel the force of gravity. So if you are wanting to do a problem that involves the gravitational force anywhere, the question is, how do you identify an inertial reference frame? You cannot follow this procedure because there is no analog of Q equals 0 when it comes to gravity. M equals 0 ain't going to cut it. Even that's going to feel gravity. Everybody see the problem? Because the solution is really going to bother you. Okay. So one of the most significant insights, that's an insight by Einstein. One of the most significant insights that Einstein made was in addressing exactly this problem. How, so remember, you get to this idea based on the equivalence principle that even massless objects feel gravity. And then you go back to this idea, which again, it played a very important role in special relativity. You need to be able to identify these things called inertial frames. Einstein couldn't figure out how to do it until he thought of this. So let me actually read my paragraph here. I'm not going to read it. So the first thing to realize, or the first thing that Einstein realized, is that of all of the forces in nature, gravity is the only one like this. Okay? For the electromagnetic force, there are definitely things that are neutral. You can use those to establish inertial reference frames. Even though he didn't know it at the time, you could also do the same thing with, say, the strong interaction. There are things that don't feel the strong interaction. There are things that don't feel the weak interaction. Actually, there's nothing that doesn't feel the weak interaction, but that's a different story. A slightly more complicated one. But generally speaking, gravity is the only thing that has this sort of universal, it affects everything in exactly the same way. So Einstein's solution was the following. He said, if gravity is the only force that is the problem child, we should just get rid of gravity. And that will solve the problem. Because if you get rid of gravity, everything works out with all the other forces. Like electromagnetism works fine. Okay? So Einstein's solution to the problem of finding inertial frames was simply, let's get rid of gravity. How do you get rid of gravity? Say it again?
Make it an acceleration.
You jump off a cliff. Okay? So, no, hold on. Here we go. Einstein realized that a reference frame which is freely falling under the force of gravity under external gravity, because we're talking about gravity coming from outside, causing this thing to fall, is our best scenario for establishing inertial frames. So let me actually draw what this looks like. Okay, so consider our picture where we have the Earth, and then we have a lab that's on the Earth, and it's sitting at rest, and we are trying to do our little electromagnetism experiment. So we've got our parallel plate capacitor all charged up. It's created this nice E field. Okay. We know that, of course, since this thing is sitting near the surface of the Earth, and it's a small lab, there's a uniform gravitational field pointing straight down. And we know, of course, that if we put a charged particle in the presence of this, and this is also, of course, going to be a massive particle, then that charged particle is going to accelerate to the right under the influence of the electric force, or the electric field, but it's also going to accelerate downwards due to the presence of the gravitational interaction, and so the charged particle is going to travel along some trajectory like so. Unfortunately, and this is of course the problem, even if we put in a neutral particle to try and establish an inertial reference frame that we can use to then, from which we can then use Newton's second law to describe this motion, the motion of this particle is accelerated downwards. Okay? But Newton's first law is telling us, wait a minute, this thing is, well, no, it doesn't work. Like, this doesn't work, period. Like, I can't establish an inertial reference frame using this. Okay? Instead, we take our lab with our experiment in the presence of a uniform gravitational field, and then we just let it fall. And freely falling means, of course, that it will experience an acceleration that is equal to the local gravitational field. Okay? In this case, how does the story play out? In this case, if I'm standing in the lab, remember, everything is happening in the lab. In the lab, this person sets up the parallel plates, they watch this charge, it does that, they watch this charge, it does that. In this lab, this person places a neutral particle between the plates of this parallel plate capacitor, and that neutral particle sits there. Why does it sit there? Because the particle is accelerating downwards at the same rate that the observer is accelerating downwards. This person, looking at that, saying it is experiencing no force, would say, hey, it's moving at a constant velocity, therefore I am in an inertial frame. Then they can take this charged particle and explain its observed acceleration correctly using Newton's second law and the electromagnetic force.
Seems simple.
So this whole strategy of using Newton's laws in an inertial reference frame, when gravity is part of the story, only works when you're in free fall. But when you're in free fall, it just goes right back to the same old story. Okay? But here's the cool part. There is a situation which is exactly analogous to this. There is a situation where you in this lab would experience the exact same thing. Whoops, deep space. In deep space, where there's no gravity, you would experience the same phenomenon. You could look at the chargeless particle, it's not accelerating, you're not accelerating with respect to it, it's an inertial frame, blah, blah, blah. So there's truly a sense in which going into free fall is removing the effects of gravity, because the one thing we know about deep space is there's no gravity. Okay? Now the key to your being able to get away with this, of course, hinges on the fact that everything experiences gravity and the gravity is universal. Okay? You couldn't play this kind of story with any other force. It's exactly because everything responds to gravity in the same way that this is even a possibility. That's, of course, one more indication, and this entire course is going to evidence that gravity is different than the other forces. Okay? All right. So the really bothersome thing that we're going to find is that the best inertial frames in a problem where there's external gravity are freely falling frames, which is pretty much the opposite of what we told students in Physics 1. But that's where this lands us. Now in all of this, there was that caveat. And that is that all of this hinged on the presence of small frames. Okay? Now, I say small, and when you think of small, you think of, like, oh, it's like 6 meters of smallness by 12 meters of smallness. That's really small. Not small. It's not big. Small is actually a statement that is a statement about space-time. The lab is a sequence of events that is extended in space due to the literal spatial size of the lab, but also it's extended in time due to the time length of the experiment. Okay? And the requirement that things be small is a requirement on all dimensions, both the space and the time. All right? Because it turns out that even if you're near the surface of the Earth, where curvature effects are small, because you're in a small lab, okay, you can devise experiments over long time periods that will actually tell you, hey, you know what, the gravity in this room is not actually uniform. Okay? All right. So I'm going to leave you with one comment that will sort of segue us into the math that is going to come at us in the next lecture. Experiments performed, and this is just a summation of everything that we've said so far, performed in a small, freely falling lab over a short time interval are indistinguishable to those in an inertial frame in empty space. Now there's a few people in the room that are going to appreciate what I'm about to say. This statement the idea that as long as you get small enough and you go to the right reference frame, that is, you let yourself really fall, that your experience of physics becomes identical to empty space. And by the way, what is the geometry of empty space if you were to make a guess? It's flat. It's like that's what special relativity is. It's the geometry of empty space. This leads us directly to the statement that the geometries we should study in general relativity are manifolds. Because one of the characteristic features of manifolds, and you are more familiar with manifolds than you might realize, the characteristic feature of manifolds as a geometry is that locally, that is, if you focus on a very small region of the manifold, it looks flat. Okay. A common example, of course, is the manifold S2, the surface of a ball. If you confine yourself to a small region and you make that region small enough, or conversely make the radius of the S2 big enough, then everything that you're experiencing looks as if it's flat. And that is, of course, what we're experiencing in this room right now. Okay. So next time we meet, we're going to get into the math of manifolds.